Okay, guys, so this is our second Flip the Classroom lesson of Chapter 2, and this lesson is going to be on logarithms, and we are going to define logarithms as the inverse of exponential functions. So to begin this lesson, we're going to talk a little bit about inverses, right? And then we're going to relate that to exponentials to define our logarithms. Okay, so when we talked about inverses previously, what we said is inverses are two functions that basically undo each other's operations, right? So let's say we've got 2x equals y. Well, right here we could say that this is the function that multiplies by 2, right? So its inverse is going to be the function that undoes a multiplication of 2 or divides by 2, right? And so right here, let's say we've got an input of 3, right? Now, for our function, we would say 2 times an input of 3 gives us 6, right? Or an output of 6. And if we took that 6 as an input of the inverse function, what we would see is that our inverse would undo the multiplication that our initial function did and give us back our 3. So right here we would see 6 divided by 2 gives us 3. Now, this is a little bit obvious, but right here what we want to point out is that the thing that our inverses are actually doing is they are switching the input and the output, right? For our 2x, we have an input of 3 giving us an output of 6, and right here for the inverse, we would take the input of 6 and get the output of 3, right? So with that in mind, we can come down and start talking about exponential functions. So right here, let's say we've got the exponential function 2 to the x equals y, right? So right here, with an exponential function, essentially the input is the exponent, right? And we take the base and raise it to the exponent. We multiply that base by itself by x times, right? So basically we multiply the base by itself by the number of times that the input tells us. So right here, for an input of, let's say, 3, right, we would have 2 to the third equals 8, right? Now right here, for our exponential function, the input is the exponent 3, and the output is the product 8. So we want to think that we're plugging in the exponent and getting out the product. Now, product is just sort of what we're going to call the output of an exponential function. It is a product, but it's not a very useful term to throw around when we're talking about exponential functions and their inverses. But basically what we want to think is that from here, the inverse function should take 8, the product, and give us the exponent of 3. So right here, we are going to take that product, right, and get out 3, the exponent. So that's what our inverse is going to do here. Remember that 3 itself is a number that's, as an exponent, is a number that's different than any other number. 3 is counting one thing, and that's how many times we're multiplying 2 by itself, right? Now, one thing we can take note of here with our exponential function is that it's really being defined by this base, right? Whenever we plug in an x value, we're going to be multiplying 2 by itself that number of times. So 2 really defines the exponential function. And likewise, we can say that the inverse, the logarithm, is going to be defined by the base 2 as well, right? So right here what we're going to say is the logarithm is going to have a base 2, and that's going to define what the logarithm is, right? That's going to define basically how the logarithm operates. Now right here, the inverse, of course, is going to take 8 and give us out the exponent of 3, right? Now the thing we want to take note of right here is what the logarithm is essentially asking us. Right here, what we're doing with the exponential function is we're taking our base 2 and multiplying it by itself x times, and we're getting as the output that product. Right here with the logarithm, we're taking that product and we're saying right here, what do I need to raise 2 to in order to get 8? How many times do I need to multiply 2 by itself in order to get the output of 8? And right here, that is the exponent of 3, right? So this is the question that the logarithm asks us. What do I need to raise that base to in order to get the input? That's the question that the logarithm asks us, and that's the way we want to think about it. So right here, if we're looking at, let's say, bring this down again, if we're looking at, say, log base 3 of something like 27, we want to remind ourselves that what the logarithm is saying is, what do I need to raise that 3 to in order to get an output of 27? How many times do I need to multiply 3 by itself? So it's, again, it's defined by that base of 3, right? But what it's asking for, or what the answer is going to be an exponent. Right? So what do I need to raise 3 to in order to get 27? That would be the exponent of 3. So log base 3 of 27 is the exponent of 3. And in general, what we want to think is logarithms really are exponents, right? When we're evaluating a logarithm, essentially what we're getting is the exponent, right? So that's how we want to define our logarithms, right? Looking at our basic sort of definition of a logarithm, we can say the logarithm is the inverse of the exponential function such that if we have b to the n equals k, log base b of k will equal n, right? And again, right here, what we're saying is, what do I need to raise b to in order to get k? Well, if b to the n equals k, then that would be the nth power. So right here, if we're looking at 3 squared equals 9, we can say, if we're rewriting this as a logarithm, this would be log base 3 of 9, or what do I need to raise 3 to in order to get 9? And that would be the exponent of 2. Right here, we've got 2 other logarithms that we use pretty frequently. The common log is log base 10, right? And in general, this log is used so often in physics and stuff like that that we don't even write the base of 10. We just sort of write it as log, right? So right here, 10 to the n equals k is equivalent to the common log of k equals n. And really, this is a log base 10. But the log base 10 is so common that we generally don't even use it. One thing that's nice about common logs is if we've got sort of 1,000 or 1,000,000 or whatever, all we have to do is count the zeros to figure out what that power is going to be. So right here, if I've got the common log of 1,000, right? How many times do I have to multiply 10 by itself in order to get 1,000? That would be 3 times. And again, you can just count the zeros to sort of cheat. Okay, the natural log is the logarithm base e. So right here, if we've got e to the n equals k, we say that the natural log would give us the natural log of k equals n. So right here, in general, since e itself is an irrational number, a lot of times when we raise e to integer powers, we're going to get irrational numbers. Really, we could say anytime we raise e to a rational power, we're going to get an approximate. We're going to have to sort of round it off because our answer is going to be an irrational number. Now, right here, if I've got e squared is approximately 7.389, that means that the natural log of 7.389 would be approximately 2. Wouldn't be exactly 2, but it would be approximately 2. Okay, so right here we've got some exponential functions and logarithmic functions that we want to rewrite. Right here, what I'm asking you guys to do is to go through and just sort of think about what this means, right? How we can think of an exponential expression as a logarithmic expression. So what I want you guys to do is to first go through and do all these. You can pause the video real quick and give that a shot. Okay, so right here we can go through and just sort of rewrite all these exponential expressions as logarithms. Some of them we can sort of evaluate and think about just as they are. Right here, log base 3 of 81 is asking me what do I have to raise 3 to in order to get 81, and that's going to be the exponent of 4, right? Right here, the common log of 1 over 100 equals negative 2. This is actually something we can think about a little bit. Right here, if I were to rewrite 1 over 100 as an exponential base 10, then right here I could say that this guy would be equivalent to the common log of, right here, I could say that 100 is 10 squared, and then if I brought that into the numerator, that would be 10 to the negative 2, right? And now right here, what I'm asking is, what do I have to raise 10 to in order to get 10 to the negative 2? and that would be the exponent of -2. We could do the same thing right here to sort of see that log base 3 of 81 equaling 4, right? You could represent this 81 as 3 to the 4th power, and then it becomes pretty clear that I have to raise 3 to the 4th power in order to get 81. So right here, the e to the 3rd power is approximately 20.8. Now this is one where you're sort of, you can type it into the calculator. We can pull up our calculator. Right here, if we pull up our calculator, we can go to the natural log, right, and evaluate 20.08, and right here press enter, and we're getting something close to 3, not quite 3. Now right here, one thing we can note is that the natural log and the common log are both logarithms that we have immediately in our calculator. For some of us, if we've got newer calculators, we've got logs of other base, and we can take a look at that as we go forward here. So right here, I'm going to get that. We can move on and talk about a kind of a crazy expression here. We've got 5 to the 7 over m power equals 2p plus 2. And right here, what we're saying is really any exponential expression I can rewrite as a logarithm. So right here, if I were rewriting this as a logarithm, the base would stay the same. I would have a base of 5. And what I would say is log base 5 of this, which is 5 basically multiplied by itself some amount of times, is going to equal the exponent 7 over m, right? So right here, if I'm saying that 5 to the 7 over m equals 2p plus 2, that means that log base 5 of 2p plus 2, right, is going to give me the exponent of 7 over m. Right here, we've got 10 to the x equals 20, and so right here, we would rewrite this as the common log, and then that would be the common log of 20 equals x. Now, this is an interesting situation. Really, what we're seeing here is if we have a variable in the exponent, right, we can solve for that variable by changing it to a logarithm, especially if our base is 10 or e, right? And we can use change of base. We'll talk about that later to evaluate logarithms as well. But right here, if we go to our calculator, we can evaluate the common log of 20 to get the x value, and that would be 1.3 approximately. So right here, we can say that we would have approximately an x value of approximately 1.3 as an x value there. This one is a little bit more interesting. Right here we've got 2 to the x equals the square root of 8. So right here what we're asking ourselves is what do I have to raise 2 to in order to get the square root of 8? Well, right here I can sort of phrase this as the question, what do I have to raise 2 to in order to get the square root of 8? And now right here, if I could represent a base of 2 on both sides, I would have what that x value would be. So right here, I can say that 8 is 2 cubed, and then right here I've got the square root, which would be an exponent of 1/2, so I could say that this would be 2 to the 3/2, right? And that gives me my x value, right? So what do I have to raise 2 to in order to get the square root of 8? That would be 3/2. All right, so here we have some logarithms, and we want to get some practice rewriting these as exponentials to sort of get the feeling of our logs. Why don't you guys pause the video and give this a shot. All right, guys, so here we have our logarithms rewritten as exponents. Again, some of these are pretty self-explanatory. It's pretty easy to see. Right here, I can say that log base 5 of 125 is the exponent of 3, and in fact, when we rewrite this as an exponent, it's very clear to see that 5 to the 3rd power would be 125. Right here I've got the common log of 1,000 equals 3, and that means that I can rewrite this expression as the exponential expression 10 to the 3rd power equals 1,000. Right here I've got log base 7 of 7 equals 1. Again, what this is asking is what do I have to raise 7 to in order to get 7, and that's the 1 power, right? So right here we can see that clearly as an exponential expression. Here we've got an interesting one. Log base 3 of x plus 5 equals 4. And just like in our previous example, right, where we saw that if we have a variable in the exponent, right, we can change it to a logarithm, and if we can evaluate that logarithm, right, we can solve for our variable, right? Here we've got a variable inside a logarithm, right? And what we're saying is if we change this to an exponential expression, we can solve for that variable. So right here we've got 3 to the 4th power. 3 to the 4th power, 3 times 3 is 9, times 3 again would be 27, times 3 again would be 81. So right here we can say that this would be 81, right, equals x plus 5, right? And right here when we subtract 5 from both sides, we are going to get right here, this is going to be 76. That can't be. No, that's right. That's right. So right here, we would say that x equals 76. And if we plug this back in, we'd get log base 3 of 76 plus 5 equals 4. And right here, that would give us log base 3 of 81. What do I have to raise 3 to in order to get 81? That's the exponent of 4, right? So something we can do, or something we can take note of for practice that you'll see very soon, is basically if we've got a variable inside of a logarithm, you can change it to an exponential and solve for that variable. Right here we have log base 3 of 1/9 equals -2. And again, right here, if I change 1/9 to, oops, that's supposed to be a -2, isn't it? If I change 1/9 to an exponential base 3, right here I could say that I've got 1 over 3 squared in the denominator, right, is equal to 1 over 9. And then right here, if I brought that 3 squared up into the numerator, that would be 3 to the -2. So we can sort of see that by representing 1/9 as an exponential base 3. That would be the exponent of 2. And right here, the natural log of 3 equals 1.099, and if we rewrite that as an exponent, we've got this guy right here. Okay, so moving on, we can go ahead and solve logarithms without a calculator. And again, right here, what we're doing is just sort of practicing that idea of what the log is asking. So right here, log base 2 of 32, now you guys might be able to do this in your head, but right here we can also think about this as the question that the logarithm is asking, which is what do I have to raise the base of 2 to in order to get the input of 32? And right here, I would have to raise 2 to the 5th power, right? So I could say that 2 to the 5th power is 32. That means log base 2 of 32. What do I have to raise 2 to in order to get 32? It's going to be the exponent of 5, right? Right here we've got the common log of 1,000. And so basically we're saying, what do I have to raise 10 to in order to get 1,000? We already solved this on the last page. That's the exponent of 3. And we've got some other questions here that are a little more interesting. So right here, if I'm looking at log base 7 of 1 over 49, right, that's the question, what do I have to raise 7 to in order to get 1 over 49? Well, right here, if I can represent 1 over 49 as an exponential, right, base 7, then I can take that exponent. So right here, let's say that's x for now, right? Now right here, I can say that 49 is x squared, right? And if I bring that x squared up into the numerator, I would get 7 to the -2, right? So that would give me, right here, an exponent of -2 as my output. Right here, we've got a little bit of a trickier one. Here I've got, what do I have to raise 8 to in order to get 16? And no, it's not 2. And you guys are smarter than that. You know it's not 2. But right here, what we can do is we can say, all right, well, let's call it x for now. And can I represent the same base on both sides? Well, right here, I know 8 is going to be 2 cubed, right? So I could call this 2 to the 3x, right? And I know that 16 is 2 to the 4th. So right here, I could call this 2 to the 4th. Now, I can sort of take this over, since I'm saying these two sides are equal, I can take this over and basically set the exponents equal, 3x equals 4, and solve for that x value, which would be 4/3. And right here what we're saying is I would have to raise 8 to the 4/3 power, right, in order to get 16. And that's how we would solve this one out. So why don't you guys go ahead and try the rest of these. Some of these aren't going to be that tricky, but you can sort of think them through, and we'll get together and try them in a second. All right, so taking a look at these guys, some of them, again, are pretty easy to intuit right here. The question that I'm asking with this first one is, of course, log base 3 of 27 is asking, what do I have to raise 3 to in order to get 27? And of course, that's going to be the exponent of 3, so that's the solution to our logarithm. This next one is a little bit easier. This next one asks basically, what do I have to raise the base of e to in order to get e to the 4th? And that's, of course, going to be 4, so that gives us the exponent of 4 as the solution. If we look to some of these other ones, we have to do a little bit more work, but they should come to us in roughly as easy a way. Right here, if I've got log base 4 of 1 over 64, right, I can represent 1 over 64 as 4 to the negative 3. So what do I have to raise 4 to in order to get 4 to the negative 3? That's going to be the exponent of negative 3, right? Right here, we've got log base 2 of the square root of 16, right? So what do I have to raise 2 to in order to get the square, I'm sorry, not the square root, but the cube root of 16. And right here what we can say is we can represent the cube root of 16 as a base of 2 to the 4/3 power, and so right here we would get 4/3 as the exponent we would have to raise 2 to in order to get the cube root of 16. Okay, so right here, logarithms as algebraic inverses of exponentials. So right here what we're saying is if we've got log base b, right, of x equals y, then its inverse is going to be the exponential base e, which raised to the y power should give us x. The relationship we're talking about here is the composition of inverses. So we know from our work with inverses that if we put an inverse inside its function, right, that the operations are going to cancel out and we'll just get the x value, right? And similarly, if we put a function inside its inverse, right, then again, those operations are going to cancel out and we're just going to get x. So right here, in general, what we're saying is if we compose inverse functions, right, functions with that inverse relationship, then all the operations will cancel out. Now, some of this we can see pretty intuitively when we look at logarithms and exponentials. For example, right here, we've got the log base 4 of, let's say, x equals y. And right here we could call what's inside log base 4 the exponential base 4, so 4 to the x equals y. And right here what we're doing is composing these two things. But we can think of this as basically just the question that logarithms ask us, and it's going to make sense when we see them cancel out. So right here what we can say is, right here, if I'm saying log base 4 of 4 to the 3rd power equals what? I'm saying, what do I have to raise 4 to? What's that exponent I have to raise 4 to in order to get 4 to the 3rd power? And of course, that's the exponent of 3. And what we're seeing here is that inverse relationship where log base 4 and the exponential base 4 cancel out. Now, a little bit trickier to see is going to be when we have a logarithm actually in the exponent. So right here, we have 6 to the log base 6 of 11, right? And this is an inverse relationship. Now, what we want to think here is, what is log base 6 of 11? When we evaluate it, it is the exponent we raise 6 to in order to get 11. So right here, if we're raising 6 to log base 6 of 11, that's the exponent we need to raise 6 to in order to get 11, right? Then basically right here, what should we get? We should get 11, right? So and we can see this probably a little bit easier with something like, let's say, log, or let's say 2 to the log base 2 of 8, right? Now, if we were to evaluate log base 2 of 8, what's log base 2 of 8? Well, right here, log base 2 of 8, we can say, would be the exponent we have to raise 2 to in order to get 8, which would be 3. So right here, we would essentially be raising 2 to the 3rd power, which would give us 8 back. And basically, again, what we're seeing is that inverse relationship, where here we have the log base 2 inside the exponential base 2, and since those two things are inverses, they will in the end cancel out and give us just our 8. Okay, so now we can talk a little bit about logarithms and exponentials as inverses graphically, right? So we've got f of x equals 2 to the x, and the inverse f to the negative 1 of x, which is inverse of f of x. Inverse f of x equals log base 2 of x. So right here, so we've got a list of inputs and outputs, right, which we can sort of plot for our exponential base 2. Basically, we're seeing the doubling function here. So right here, we can say that we've got a horizontal asymptote, we know, for an exponential function at 0 in this case, right? And right here, with an exponent of negative 2, we would get an output of 1/4, basically dividing two 2's. Exponent of 1 would be basically dividing 1 2. Right here, if we're multiplying no 2's, then that's going to give us 1. If we're multiplying 1 2, we get 2. 2 2's, we get 4. And so right here, we can sort of see this kind of a graph from our exponential base 2. If we raise 2 to the third power, we would get 8. So we should get that guy right there. And that would give us this. Now, if we sort of highlight these points and think about what an inverse is going to do, what we can say is we know that the inverse is going to switch every x and y, right? So right here, graphing these points, we say for an x value of 1/4, we're going to get a y value of negative 2. For an x value of 1/2, we are going to get a y value of negative 1. For an x value of 1, we would get a y value of 0. And for an x value of 2, we would get a y value of 1, and for an x value of 4, we would get a y value of 2. If we had an x value of 8, we would get a y value of 3, right? And in general, what we can see here is that instead of that horizontal asymptote on the x-axis with the inverse, we see a vertical asymptote on the y-axis, and the graph of our logarithm is going to look like this. Now, an important thing to note here, this is a very, very steep vertical asymptote. So when you see it on the calculator, a lot of times it cuts out. You don't get to see the whole thing. But you need to remember that it's the inverse of an exponential function, and the exponential function's domain is going to be negative infinity to positive infinity. So that means that the range of the logarithmic function is going to be from negative infinity to positive infinity as well. Basically, we're seeing every single y value, and as this logarithmic function sort of stretches out along the x-axis, it also sort of creeps up to positive infinity there. So right here, let's go ahead and erase the exponential function and talk about the graph of the logarithmic function that we're seeing here. Right here we can say that the domain of the logarithmic function is going to be the range of the exponential function. And we can see that in our graph, right? The range of the exponential function goes from that horizontal asymptote of 0 up to positive infinity. And right here we're seeing a domain for our logarithm of 0 to positive infinity. Right here, the domain of the exponential function we just stated, negative infinity to positive infinity, and that means that the range of the logarithmic function is going to be negative infinity to positive infinity. Since we're switching all the x and y values on our ordered pairs, we can similarly say this guy's increasing on his domain, right? So basically, from 0 to positive infinity, we're always increasing. We increase slower and slower and slower, and we creep up to positive infinity, which is really sort of counterintuitive, but that's how it works. Is it bounded? No. Right here, the range goes from negative infinity to positive infinity. Is there any extrema? No. Right here, asymptotes, we have a vertical asymptote at x equals 0, right? And the end behavior here is only going to stretch out in one direction. We talked about this a little with our 12 basic functions. We can say right here, and again, we should just call this guy f of x, really. And here we can say this guy is f of x equals log base 2 of x. As x goes out to positive infinity, we're going to positive infinity. And there is no end behavior in the negative direction since our domain cuts off at 0. Right here, we can talk about a transformation of log base 10. You can graph this guy in the calculator. Incidentally, one of the things we want to take note of right here when we're talking about the domain of a logarithmic function is the last restriction of our domain with regards to functions in general, which is no negatives or 0 in a logarithm. Right? So that means right here that this guy can't be negative or 0. X plus 1 can't be negative or 0. And what we'll see right here, if we think about this as a translation, is basically that vertical asymptote moved from 0 to negative 1. And right here, if we were to sort of get a rough graph of this guy, he would look something like this. And he would be pretty steep coming out this way, right? Again, domain. Why don't you guys go ahead, well, I mean, it's not much to analyze all this. Right here, the domain is going to go from 1 to positive infinity. The range, of course, is negative infinity to positive infinity. Increasing on its domain. And right here, decreasing node, is it bounded? No. And then right here, no extrema. And we can now say that we've got an asymptote, but this asymptote is going to be at x equals negative 1, right? From our transformation there. And right here we can say the limit of our f of x, in this case, as x goes out to positive infinity, is still positive infinity. Okay, so transformations here. We talked a little bit about these transformations. Why don't you guys go ahead and pause the video and try some of these transformations on your own, and then we'll come back and talk about what we're seeing with these guys. All right, guys, so we're starting out with the graphs. I sort of traced these guys and brought them down. And now we want to talk about the transformations of these graphs. So right here, initially what we can say with our p of x right here, which is a transformation from our f of x, is that we are adding 2 inside the logarithm, which is going to shift us to the left 2. Right? So we're moving 2 in the negative direction, right? And basically that means our vertical asymptote is not going to be on the y-axis anymore. It's now going to be at negative 2. So we can see that there. And now right here, that multiplication of 3 is a multiplication of a whole number outside the function of log base 2. And what that is going to mean is that this guy is going to be vertically stretched. So right here, we've got an output of, let's see if we can sort of make this right. If we say this guy, if we say we've got this point right here, he's going to be 3 times his normal value, so that's going to be 3. And then right here, if we go out to 4 away from that vertical asymptote, so that would be right about there, we should have, that's 3, isn't it? That's 3, so this would be 4. That would be, that would go from an output of 2 to an output of 6. So right here, we can sort of get an idea of that trajectory. Now, I'm not going to ask you guys to be that accurate with these, but in general, we want to know what's happening with these stretches. And basically, we'd see a stretch that looks something like that, right? Vertical stretch. Now, right here, we're going to have to do a little bit of work. We've got the natural log of negative x plus 2. And if we remember our transformations, when we're evaluating those transformations, we want to factor that negative off of the inside of the function to evaluate what we're seeing. So first, actually, what we're going to see is a horizontal shift that is 2 in the positive direction, right? So from that subtraction 2 that we get when we factor off the negative from the inside of the function. So now we've got a vertical asymptote of positive 2. And then from that negative, right, we can consider this a reflection across that vertical asymptote of x equals positive 2. So I'm going to flip this guy. I'm going to flip them from left to right. And that's going to give us a graph that looks something like this. Right? So that would be the graph of our natural log of x plus 2. You can go ahead and type it into the calculator and check. All right, so right here, our last logarithm, again, you can type this guy into the calculator just like the natural log. And our last logarithm is going to be a common log, and right here we're saying that first we are subtracting it from 3, so that's going to mean 2 things. One thing we can say here is that this is going to be a common log that's negative, and we could say that that's a positive 3, so we could think about it as a plus 3 at the end. Our common log being negative on the outside means that we are going to see a vertical flip. So right here, this means we're flipping across the x-axis, up to down. Ooh. So right here, we'll move this guy up, and we'll see a graph with something like this. And then right here, that addition of 3 is going to take us up 3. So I'm going to try to move this point, which is my 0, up 3. 1, 2, 3. Is not a very convincing 3, but we can sort of try and make it a convincing 3. And basically, I've moved this graph up 3 to about right there. Maybe I can erase a little bit here to fix this guy. Somewhat didn't really work. But right here, you guys get an idea of the graph. And basically, again, it's the same transformations you guys have seen before. So that's the entire lesson we've got right here. My plan is to give you guys a worksheet after Parents' Weekend, so we'll come back doing some work and looking at logarithms. I'm sure you guys have seen them from last year, so a lot of this might be review. We'll talk about what I expect, we will have talked about what I expect from you guys for this stuff before the long weekend anyway, so we can go ahead and give that worksheet a shot when we get back. Okay, guys, have a good Parents' Weekend.